In this short video, let's take a look at this problem of aggregating the VaRs or the value at risk across products, business lines, or various divisions of a financial institution. I'm assuming here that there is a financial institution which, let's say, has n product lines or n, let's say, divisions within it, each one of which, let's say, is computing its VaR separately. Okay, so I'm assuming that the current valuation of, let's say, the total portfolio, let's say, of each of these divisions stands at V1, V2, V3 all the way till Vn. These divisions, let's say, are modeling the P&L or the return, individually speaking, and they are, let's say, plotting a distribution of these P&Ls or returns, and from that distribution they are estimating their own VaR. Now, we'll be making a number of assumptions as part of getting to this aggregate VaR formula, and these assumptions are indeed ones that you need to keep in mind when you apply this formula in any given context. Okay. The first assumption which I am making here is that the individual VaRs which are being estimated by each of these divisions, for example, are relative VaRs, or for that matter, let's say these are VaRs which are relative to where each of these divisions expect themselves to be at, let's say, at the end of the horizon which has been chosen for these VaRs. Now that is what we call relative VaR. To make it even simpler, you can assume that the VaRs are estimated using an assumption, let's say, of a zero mean, for example. Okay, so therefore, let's assume that each of these divisions are working with returns, let's say. Let's next assume that each of these divisions are imposing a normal distribution assumption on these returns, and based on, therefore, a chosen confidence level, each of these divisions are estimating the VaRs to be, let's say, these amounts. Specifically, it's the Z corresponding to the chosen confidence level, that times the volatility of returns, and that times the current valuation of these businesses, for example. Okay. Now, that's where we stand. We have the VaRs for each of these n divisions or business lines, and we want to aggregate these VaRs to somehow get to a VaR number at the same confidence and using the same horizon as the individual VaRs. And this aggregate VaR number is what we refer to as the firm-wide VaR. Okay. Now let's do this. Let's do it from scratch. So if I had to get to this VaR number, which is a number which is for the entire firm, I would need a way to somehow aggregate the individual components which go into this VaR. Had I been working with the PL of each of these individual business lines, I could have aggregated the PL, very simply put, just add all the PLs together. That would have given me the PL for the entire portfolio of these businesses. Okay. Now, I can convert this aggregation of PL to actually aggregation of returns. How would you do it? Each of these PLs, remember, is the final valuation of these businesses at the end of the horizon minus the current valuation. I have just included in the subscript V1 also the time at which it is applicable. So V10 would be the valuation, let's say, as of today. V1T would be the valuation at the end of the horizon. So for any business line, you will have PLI will be the valuation of this ith business at the end of the horizon minus the valuation as of today. If the valuation at the end of the horizon is the valuation as of today, that times 1 plus a random return, then this is what you get, and therefore the PL is, very simply put, the current valuation, that times a random return. Okay, and therefore I can substitute this back into this formula, and I get that the PL for the entire firm is equal to valuation of the first business, that times the random return of the first business plus V2, R2, and so on. Okay, I can write down the total PL to be equal to the total value of the firm, which is, let's say, V1 plus V2 plus V3 all the way till Vn, that times the random return at the firm or portfolio level. Okay, so this gives me my aggregate return to be very simply V1. I've taken the VP on that side upon V1 upon VP, that times R1, and so on. Okay. Now this is something that you could have written intuitively as well. Okay. You could have written it as the aggregate return. Just, this relation which we borrow from portfolio theory is simply the weighted average of individual returns, as simple as that, where the weights are simply the current valuation of this business line, that divided by the total firm-wide valuation, VP. Okay. This is an assumption which I have already made, and that is the individual return of any business line is normally distributed. I am assuming parameters here of mu I for the mean and sigma I for the volatility or standard deviation. Now that I have this relation which tells me what the portfolio return will be, estimated from the individual returns, I can very well now arrive at the distribution of the portfolio level return. You will have to appreciate this at this point in time, that because of our choice of normal distribution for each of these individual returns, we automatically get that the portfolio level return is also normally distributed. Remember, if you combine a number of normally distributed random variables using a linear kind of a mixture like this, then the final random variable that you arrive at is also normally distributed. It's a very welcome and attractive property which a normal distribution offers to you. This property may not be available to you if, let's say, you had chosen individual returns to be distributed using some other distribution, let's say uniform distribution. Okay. So if this portfolio or firm-wide return is normally distributed with this as the mean and this as the standard deviation, just go back to portfolio theory and write down the expressions for the mean and the standard deviation. This would be a weighted average of means, and this would be this expression which combines some weights of the individual variances, and then you have the covariance style terms coming in. Okay, these are both expressions from portfolio theory. Now let's do this. Start from this expression. I know that my portfolio or firm-wide returns are normally distributed with this as my distribution. Based on this RP, I can very well arrive at very quickly the firm-wide VaR, and that simply is the ZC corresponding to the chosen confidence level, that times the portfolio volatility, and that times the total valuation VP. Okay. Now, this sigma P is now what we will replace here with its formula. Okay. Again, in writing down this VaR, I am assuming it's a relative VaR, or you can say it's a VaR assuming that the mean is close to a 0. Okay. So if I write down or replace this sigma P with its expression, then my formula becomes this. I have replaced it here. Take the ZC VP inside the square root. It enters as a square. That means it enters as ZC square VP square. And what I have done here is I have combined the W's and the VP's. Remember how W's were defined? The ith weight was the value of the ith business that divided by the total value of the firm. So whenever you combine the W and the VP, you get the individual firm-wide value, individual business-wide valuation. Okay. So this guy will be V1 square. W1 VP is V1, W2 VP is V2, and so on. Okay, that's what I have done. Next thing which I have done is just combine the ZC, V1 and the sigma 1, because I know the product of these three is VaR1. Okay, so wherever the ZC, the V and the sigma appear, you can replace it with the individual VaR. What you then get is the formula for aggregating the VaR across the entire firm, and that looks something like this. You will have VaR1 squared plus VaR2 squared all the way till VaRn squared. These are n terms. Plus you will have the cross terms. Okay, these are terms which will have VaR1, VaR2, VaR2, VaR3, and so on. Okay, so these are NC2 or n into n minus 1 by 2 terms. Okay, so these are all the VaRs taken in a pairwise manner. And these terms, they include the correlations. Okay, so these correlations are the correlations between the returns of the individual businesses pairwise. Okay, now this is the formula that we were aiming at. This formula looks like the standard deviation formula from portfolio theory for the standard deviation of a portfolio. I mean the standard deviation of returns of a portfolio. But the only thing different here is there are no weights here because we are already working with dollar numbers. Okay, so weights were there in the standard deviation formula because the weights represented the allocation of $1 into various assets. Okay, so here we are already working with dollar numbers. There are no weights here. They have already been incorporated into these terms. Okay, other than that, it looks and feels the same. So the attractiveness of this formula is that you don't have to really generate a firm-wide distribution to work out this number. You can let the individual businesses work out their respective VaR numbers, and then you can just combine these numbers using this formula to arrive at the VaR for the entire firm. There were a number of assumptions that went into this. The first one was that we referred to a relative VaR and or a zero mean assumption. That was my first assumption. The second and a very important assumption was that we focused on and limited ourselves to a normal distribution, because in this choice of distribution, the final portfolio or firm-wide distribution of the P&L or the returns matches the choice of distribution for the individual P&Ls or returns. Okay, so that was a very important assumption. And then we also assumed that the firm-wide VaR is computed using the same confidence level and horizon as the individual VaRs. Okay, now if the first assumption is violated, let's say I do want to work with individual VaRs that have taken into account the mean, for example, then using this formula will not be exact the way it is when this assumption does hold good, but it won't be that bad. Okay, so that is something to keep in mind. If the first assumption does want you to incorporate a mu and you use this formula, you won't be that way off. You won't be exactly accurate. Keep that in mind. Okay, now the next one, this formula is what we've written for and we want to apply it to the VaR. Now we can ask this question, can this formula be extended to even the expected shortfall? Now expected shortfall we know is like some kind of a weighted average of VaRs which are computed at confidence levels that exceed the C at which you want to compute the ES. So since ES is like some kind of a weighted average of VaRs in the tail, and we are combining together VaRs using this formula, somehow we can intuitively sort of agree that this formula can be somehow extended to even work with the ES as well. Okay, so we are saying here that if you have expected shortfalls that your each business line have computed for themselves, and you want to somehow aggregate these expected shortfalls to arrive at the total ES for the entire firm, then you can use a formula which looks something like this. It looks something like ES1 squared plus ES2 squared, blah blah, till n terms, plus 2 ES1, ES2, row 1, 2, plus 2 ES1, ES3, row 1, 3, and so on. Okay, so this short video, basically it helped us take a look at how we get to the formula which aggregates a number of VaRs together to arrive at the firm-wide VaR. And we, most importantly, took a look at what assumptions need to be satisfied for this formula to hold exactly true. Okay.